this is the step which is obtained by applying this modification but there is an error, there is a mistake, that minus 1 square is missing here. So you have to write minus 1 square as the second term on the left side of the congruent symbol, and after that you can then you factorize the left hand side. It's because now we have the left hand side as a square minus b square is congruent to 0 mod p. The left hand side itself is a square minus b square. Now you can factorize that a square a minus b into a plus b. You can factorize a minus b into a plus b, and then we get that n to the power of p minus 1 by 2 minus 1 into n to the power of p minus 1 by 2 plus 1 is congruent to 0 mod p. What is the result of this? That hence this statement can imply that it can imply two congruences. The first congruency is n to the power of n raised to p minus 1 by 2 minus 1 is congruent to 0 mod p. Either this statement or the second statement, n raised to p minus 1 by 2 plus 1 is congruent to 0 mod p. Either the first one or the second one will be correct. Both can also be correct, but in general you can say that either the first statement or the second statement will be true. So that is the outcome of this little Fermat's theorem. Using little Fermat's theorem, thus we get that, and by simplifying that you will get n raised to p minus 1 by 2 is congruent to either plus 1 or minus 1 mod p. Okay, that is the important thing which we will find an important application in the proof of the Euler's criterion. Now we are coming to the Euler's the important result, the Euler's criterion. Let's read that the statement of the proof, the statement of the result. Let's read it, and that starts with a prime number. By taking we can begin that statement by taking a prime number. Let p be an odd prime. We consider an odd prime p, and then for all n, for every n, we consider any natural number n. N bar p will be equal to n raised to p minus 1 by 2. No, this is not equal to, it is congruent to the n bar p. N bar p is the Legendre symbol. Okay, and that quantity is equal to n bar p is congruent to n into the power of p minus 1. Here that the actual expression is missing here. It is it goes outside the range of the visible range. So actually the expression is n raised to p minus 1 divided by 2. So this theorem can be used to find the Legendre value, Legendre symbol value for a given number. But this is very useful when the value of n and p are much small. In the case of big values, you will find some difficulty in applying this. So the use of this result is explained here. Once again, let's go through the statement of the result. If let p be an odd prime, and then for any natural number n, we have n bar p, the Legendre symbol n bar p is congruent to n raised to p minus 1 by 2. We are now coming to the steps in the proof. Okay, we have divided the proof into different cases. In the first case, see, we have the first case of or the beginning. In the beginning, we have the first case that in this case we consider the Legendre symbol n bar p. We assume that, let's assume that n bar p equal to 0. So when when we are going to get the n bar p equal to 0, you know that this can happen only if n is divisible by p, right? So when n bar p, when the Legendre symbol n bar p equal to 0, that means p can divide n. So this is true. Therefore n is then congruent to 0 mod p, right? right? Okay, this is true. N is congruent to 0 mod p. Now we can using this statement, using this congruence equation, we are going to take the p minus 1 by 2 the p minus 1 divided by 2 to the power of that congruence equation. In other words, we are going to take the p minus 1 by 2 the copies of p minus 1 by 2 copies of that the same statement, and then we can multiply them together. Thus we can obtain n raised to p minus 1 by 2 is congruent to 0 raised to p minus 1 by 2. So this is by multiplication, by applying the multiplication rule of congruence equations. So we get that the quantity that 0 raised to p minus 1 by 2 is congruent to mod mod p. Therefore we get n raised to n to the power of p minus 1 by 2 is congruent to 0 mod p. Here we get 0. Okay, then what? And then replacing therefore you know that in this case n bar p equal to 0. So you can replace this part here. Since we get 0 here, you can replace this 0 by that quantity n bar p in the first case only. So we get that n raised to p minus 1 by 2 is congruent to n bar p. Okay, n bar p in bracket is required here, n bar p mod p. After completing that first case, we are coming to the second case. Let's consider the second case. In this case, we assume that we consider that n bar p equal to 1. That means the Legendre symbol value of n bar p equal to 1 means n is then a quadratic residue mod p. So we know applying that definition, we can say that in this case n is quadratic residue mod p. When n is quadratic residue mod p, we know that using the definition of quadratic residue mod p, we can say that the equation, when we consider the equation x square is congruent to n mod p, this equation has at least one solution, right? When it has a solution, then it has one more solution. So the solution, so it has a solution. In this case, we can say that undoubtedly we can say that the equation x square is congruent to n mod p has a solution. And we consider such solutions. Then when we consider such solutions, it has solutions. Then when we consider the solutions, and for that solution, and we take the power. Okay. Okay. No. For such values of n, then there exists some set of values for n for which this kind of equation has solution. When we have that, when we know that when we can have solutions to this equation, and we know that whenever n is a quadratic residue mod p, only when n is a quadratic residue mod p, you are going to have a solution for this equation. That also we know. You can recall that. Okay. So when we are now considering only such cases, here in this case, the second case means that we are considering only those n's for which the quadratic equation x square is congruent to n mod p has solution. Then we are now going to the next step by taking p minus 1 by 2 to the power. We are taking taking p minus 1 by 2 copies of the quadratic equation, and then we multiply them together, and then we get that x square the whole raised to p minus 1 by 2 is congruent to n raised to p minus 1 by 2 mod p. We get x square the whole raised to p minus 1 by 2 is congruent to n raised to p minus 1 by 2 mod p. Okay, and this is obtained by multiplying p minus 1 by 2 copies of the quadratic equation, and then simplifying, we get that x raised to p minus 1 is congruent to n raised to p minus 1 by 2 mod p. So this x raised to p minus 1 is congruent to n raised to p minus 1 by 2 mod p. But the solution, when we think about the solution also for this quadratic equation, whenever this equation has a solution, that solution will also belong to the range 1 less than or equal to x less than or equal to p minus 1. right? Then it belongs to the range 1 less than or equal to. Okay, not only that, it belongs to that solution, then can belong to the range of numbers 1 less than or equal to, yeah, x less than or equal to p minus 1. That's correct. And so for those values of x, we know that since p is a prime number, for those values of x, okay, for those values of x, x cannot be divided by p, or p cannot divide x for those x in this range. If you consider this range also, then and as a result, by applying that Fermat's little Fermat's theorem, applying again in the little Fermat's theorem, we can say that x raised to p minus 1 is congruent to 1 mod of p. So when do we get this? And this particular situation we have when n bar p equal to 1. So thus, since we get that using this x raised to p minus 1 is congruent to 1 mod of p, now you can replace, since we already have x raised to p minus 1 is congruent to n raised to p minus 1 by 2 mod of p, and we now again we have x raised to p minus 1 is congruent to 1 mod of p. Now we can combine these two, the above equation, congruency equation, and now currently obtained congruency equation can be combined to obtain that n raised to p minus 1 by 2 is congruent to 1 mod of p. Okay, thus we can conclude, we can make a conclusion in about that the second case. So whenever we have n bar p equal to 1, we get that n raised to p minus 1 by 2 is congruent to 1 mod of p. Okay, then we are coming to, we can now begin the discussion on step on case 3. Coming to that case 3, we can take that we can assume that the Legendre symbol in this case equal to n bar p minus 1. The Legendre symbol value is n bar p equal to minus 1. See, bracket is missing. N bar p equal to minus 1. We just assume that. That means n is then not a quadratic residue mod of p. Okay, then n is not a quadratic residue or quadratic non-residue mod of p. Then n is a quadratic non-residue mod of p. Okay, therefore the equation x square is congruent to n mod p, x square is congruent to n mod p has no solution in this case. Next, you are asked to consider a function. You are asked to define a function fx equal to, we are considering a function, we are defining a function fx equal to x raised to p minus 1 by 2 minus 1. Fx equal to x raised to p minus 1 by 2 minus 1. Okay, and then the degree of this equation is, it is p minus 1 by 2. Degree of this equation is p minus 1 by 2. Now we are going to make a congruence equation using fx. The congruence equation is fx is congruent to 0 mod p. After considering this congruence equation, fx is congruent to 0 mod p, you can think about the degree, its degree equal to p minus 1 by 2. Then actually it is x raised to p minus 1 by 2 minus 1 is congruent to 0 mod p, and hence we get that x raised to p minus 1 by 2 is congruent to 1 mod p, and by rearranging this term, by transferring this term to minus 1 to the right side, we get that x raised to p minus 1 by 2 is congruent to 1 mod p. And let's think about the solutions of all possible. Let's think about the solutions of this equation. As this is a congruence equation, you know that the maximum number of possible solutions for this equation is p minus 1 by 2. So this equation, this congruence equation can have maximum p minus 1 divided by 2 solutions. But we know that whenever n is quadratic residue mod p. Also you can remember this point is an important point. And if n is quadratic residue mod p, we know that n raised to p minus 1 by 2. Here in our previous discussion we have seen, in the previous case, in case number 2, at the end we have seen that n raised to p minus 1 by 2 is congruent to 1 mod p. Okay, and that happens whenever n is a quadratic residue mod p. And we know that there are p minus 1 by 2 such numbers. The what kind of numbers? There are p minus 1 divided by 2 numbers which are less than p, and that are also quadratic residue mode p. So clearly we can say that at this point, using that fact, you can conclude that this equation has since it has maximum p minus 1 by 2 solutions, it has now exactly p minus 1 by 2 solutions, and those solutions are the numbers which are quadratic residue mode p. So if you are considering the numbers, we know that we are considering here the numbers from starting from 1 up to p minus 1 to decide whether the number is a quadratic residue or quadratic non-residue. See, we know that exactly p minus 1 by 2 of these how many numbers? These p minus 1 numbers, total number of p minus 1 numbers are there. Out of these p minus 1 numbers, we know that p minus exactly p minus 1 divided by 2 numbers are quadratic residues, and the remaining numbers are quadratic non-residues. Those quadratic residue numbers can satisfy the equation x raised to p minus 1 by 2 is congruent to 1 mod p that we have seen. So for thinking about, you can now think about those numbers which are not quadratic, which are quadratic non-residue mod p. For those numbers, they are not solutions of this equation, because those solutions, the number of solutions, then we are all the solutions are decided by those quadratic residue numbers. So whenever a number is a quadratic non-residue, that cannot be a solution to this equation. So if you are taking a number which is not quadratic residue, or which is a number quadratic non-residue mod p, then you are going to get when you substitute that number in this equation, when you substitute it in this equation, you are going to get not equal to, in this case, non-congruence here, because that equation is not satisfied, it is not balanced. So you are going to get, if you are considering such numbers, you are going to get that x raised to p minus 1 by 2 is not congruent to 1 mod p, right? Okay, so that is the important point that we want to note at this moment. X raised to, for those numbers which are quadratic non-residue mod p, when we substitute that number in this equation, you are going to get x raised to p minus 1 divided by 2 not congruent to 1 mod p. Okay, now we can now okay, and thus we have for those since we have for those numbers, we can now think that number is n. Okay, and that number we mean n. We can take that number which is not a solution of this equation. That means n is, we can now suppose that n is a number which is quadratic non-residue mod p. Suppose n is quadratic non-residue mod p, and when then if we then substitute the n in this equation, then we get that n raised to p minus 1 divided by 2 is not congruent to 1 mod p. Okay, once again I shall repeat, n raised to, for that numbers, for such numbers, n raised to p minus 1 by 2 is not congruent to 1 mod p. So okay, that situation is written here. Here we have n raised to p minus 1 by 2 is not congruent to 1 mod p. And also I can repeat that that situation happens whenever the Legendre symbol value n bar p is equal to minus 1. See, whenever n bar p equal to minus 1, you are going to get that n raised to p minus 1 by 2 is not congruent to 1 mod p. But you can now come back to the previous discussion that we had just before that, just before the beginning of that the theorem, and that is that this is that point, that is n raised to, only two possible values are there for n raised to p minus 1 by 2 congruent n raised to p minus 1 by 2 congruent to some x, if you are taking here x mod p, and those values are plus 1 or minus 1. See, so this is the situation. This situation is there when n is a quadratic residue mod p. That we have completed that discussion. We have completed all those discussion in section or in case 2. As part of case 2, we have completed the discussion. When does it happen? It happens if n bar p equal to 1. So then we have n quadratic residue mod p, and then we get n raised to p minus 1 by 2 is congruent to 1 mod p. In the remaining case, we have n is quadratic non-residue mod p, and then we have n bar p equal to minus 1. But that is the remaining case, and the remaining, in that case we know that we have just proved that n raised to p minus 1 by 2 is not congruent to 1 mod p. In that case, in the case number 3, we have proved that n raised to p minus 1 by 2 is not congruent to 1 mod p. Then to which quantity it can be then congruent? It must be then congruent to minus 1. So if you want to correct that non-congruence to a congruence relation, then you have to correct it equal to rewrite it equal to minus 1, because the only two possible congruence equalities are there with respect to n raised to p minus 1. The first value belongs to the case 2, and the second equality belongs to the third case. In the third case, thus we have n raised to p minus 1 by 2 is congruent to minus 1 mod p. Thus we can conclude our result. Therefore, in all these cases, you can see that in the second case also, n raised to p minus 1 by 2 is congruent to 1 mod p. See, in that case, in the beginning we have taken n bar p equal to 1. Therefore, this 1 can be replaced by n bar p. Thus, in the case 2, we have n raised to p minus 1 by 2. Finally, we get that it is congruent to n bar p mod p. Here also, we have since in the case 3, n bar p equal to minus 1. Therefore, since we get that n raised to p minus 1 is congruent to this is then n raised to p minus 1 by 2 is not congruent to 1 mod p. Therefore, it must be congruent to n raised to p minus 1 by 2 must be congruent to minus 1. But minus 1 is equal to n bar p in this case. Therefore, you must write that in the third case, you must write that n raised to p minus 1 by 2 is congruent to n bar p. Thus, in all the cases, in all the three cases, we get that n raised to p minus 1 divided by 2 is congruent to the Legendre symbol n bar p mod p. And okay, this is this way we can complete the proof of the result. The result is known as the Euler's criterion. Okay, next we have to discuss another result. That result says that the Legendre symbol n bar p, the Legendre symbol is a completely multiplicative function. The result says that the Legendre symbol is a completely multiplicative function. Legendre symbol here it is taken as n bar p. It's where n is a given natural number, then n bar p is a completely multiplicative function. In order to prove this, what we want to do, we want to select two natural numbers m and n. Any two natural numbers m and n we have to select, and then you have to show that the Legendre symbol of m into n bar p equal to Legendre symbol m into n bar p is equal to the Legendre symbol m bar p into Legendre symbol n bar p, and this is the thing that we want to show. Okay, and that can be done by dividing the entire proof into different cases. In the first case, see, we have in the first case we can assume that p divides n. This situation is possible. See, we are taking two numbers m and n. We are considering two numbers m and n, and the situation in the first situation we assume that p divides n or q divides n. You just suppose that either p divides n or q divides n. If p divides n, then n bar p equal to 0. If q divides if p divides m, then you have to take that m bar p equal to m bar p equal to 0. Thus, if p divides n or p divides m, you have then m bar p equal to 0 or n bar p equal to 0. Then what about m into n? If p divides m or p divides n, assuming that p divides m or p divides n, then you can say that p divides the product m into n. then the p and then the number p divides the product m into n. So it is clear that m into n bar p is equal to 0. Thus m into n bar p, m into n bar p, see here, m into n bar p, the Legendre symbol value equal to 0. And that can be then written equal to mn bar p equal to 0 into 0. You can write 0 into 0, and that will be then it can be replaced by it's equal to 0 into 0. That can be then replaced by the quantities m bar p into n bar p. You can write that it is equal to m bar p into n bar p in that case. Thus we have the result correct in the first case. Next we can consider the case either p divides n, p does not divide n, or q does not divide m, and that is the situation. The case 2, we have either p does not divide n or p does not divide m. Okay, then you can write that n bar p then equal to either plus or minus 1, or m bar p equal to plus or minus 1. Then n bar p equal to plus or minus 1, or m bar p equal to plus or minus 1. Then consider the Legendre symbol and by the previous result, by you know, then you can consider the Legendre symbol and using the previous result. The previous result means Euler's criterion. Using the Euler's criterion, you can write that n bar p equal to n raised to p minus 1 divided by 2 mod p. Also m bar p equal to m raised to p minus 1 by 2 mod p. You can write both expressions, and also you can write m into, you can think about, you can consider m into n bar p. When we consider m into n bar p, then you can apply the same result. Applying the same result, you can write it that m into equal to m into n the whole raised to p minus 1 divided by 2 mod p. M into n raised to p minus 1 by 2 mod p. Okay, and next you can separate this. You can write it as the product of two powers of the powers of two numbers, and that is then m into n bar p is equal to m raised to p minus 1 by 2 into n raised to p minus 1 by 2. By splitting this, you get that m raised to p minus 1 by 2 into n raised to p minus 1 by 2, then mod p. You can with respect to mod p. Additionally, you know, since m bar p equal to this thing, we have once we have discussed this thing, m bar p equal to m raised to p minus 1 by 2 mod p, and n bar p equal to n raised to p minus 1 by 2 mod p. And what we can do next, you know, you can then you can combine by multiplying these two, and you can name them equation 1 and equation 2. After that, you can then multiply 1 and 1 by 2. You can multiply using you can multiply, you see this is okay, this is actually congruence. There is a mistake. This is Euler's criterion says that this is congruence. These are mistakes. Here m bar p is congruent to m raised to p minus 1 by 2. Here also you have n bar p is congruent to n raised to p minus 1 by 2, right? Yes, that is you have to correct that. There are erase. M bar p, mn bar p is congruent to, actually these are congruent to 3 lines must be used. And here also, here we have all these, wherever we apply that Euler's criterion, you have to correct it. Not equal to, you have to write congruence. Thus we have now by multiplying, using the congruence multiplication, we can obtain that m bar p into n bar p is congruent to, here symbol must be changed, congruent to n raised to p minus 1 by 2 into m raised to p minus 1 by 2, then mod p. But here again mn bar, then again considering mn bar p, mn bar p, you begin a new statement, a new step by considering mn bar p equal to mn raised to p minus 1 by 2, that is then congruent to, this quantity is then congruent to mn raised to p minus 1 by 2. See, here we have mn raised to p minus 1 by 2, and this is the, then coming to this expression, the previous equation, referring that previous equation, here you have this quantity equal to this quantity, but you know, you are going to, you can we are going to convert this expression into the left hand side, so you have to replace that, you have to use a congruent symbol here. Actually here we have congruence, therefore when you write this expression, mn raised to p minus 1 by 2 must be then congruent to m bar p into n bar p, m bar p into n bar p. So okay, I don't know, this here we have actually equal to, because here we simply separate, we factorize here, since we factorize this m raised to p minus 1 by 2 into n raised to p minus 1 by 2, that's okay. But when after this step, you have to, after this point you have to write the congruence, actually that's also a mistake. Here actually we require ordinary equal symbol, but here we require congruent symbol, because you are going to apply that congruence here, and therefore here we have congruence, the congruence of m bar p into n bar p, then mod p. You know, then Legendre symbol is then complete. Therefore, Legendre symbol is complete. But this is not the end of the proof, because we need to show that, we want to show that mn bar p is equal to m bar p into n bar p into n bar p. Okay, but we have just proved that mn bar p is congruent to, we have proved that mn bar p is congruent to m bar p into n bar p mod p, and this is not a step where you can say that where you can conclude that the Legendre symbol function is is completely multiplicative. You need to show some more facts about the some more points about the last expression that we have derived. The last expression that we have derived is mn bar p is congruent to m bar p into n bar p mod p. Okay, this is called for the equation of 4, or the line 4. Then in order to establish the equality, see here the congruence, here we have only the congruence relation connecting left hand side and right hand side. Actually we need to replace that congruence relation by equality relation. For that, you know, you have to show that left hand side of the congruence is equal to right hand side of the congruence, and by removing modulus p. But for that you can you have to consider all possible values of, we can do that by considering all possible values of the left hand side and right hand side, and then you can compare it with the you can compare these values with each other, and whenever the left hand side value, whenever we have a value for left hand side, if that value is equal to the right hand side value that you are going to get, then you can say, well, then you can say that the left hand side is equal to right hand side. See, I shall repeat. So we have to consider all possible values of the left hand side and right hand side of the congruence. So see, we know that here we have, since this is a congruence, so we have the values 0, plus 1 or minus, and since this is the Legendre symbol, the left hand side is the Legendre symbol value, we know that it has values either 0, plus 1 or minus 1. Here also we have, on the right hand side we have the values here, the first quantity can be 0, plus 1 or minus 1. Similarly, second quantity can also be either 0, plus 1 or minus 1. So by combining, we have to consider all possible values for these three numbers, and you have to compare the left hand side and right hand side by considering all these possible values, and you have to establish the equality in all the situation. You have to consider, in short, you have to consider all cases, all possible cases of various values of the three quantities, three legendary symbol values that are appearing in the equation, that are used in the equation. Then you have to establish the equality in all the cases. Okay, and that can be done. You can see that is done here. Okay. For doing that, first we transfer the quantity, the right side quantity, into the left hand side, and then what expression we are going to get, you get that mn bar p is minus m bar p into n bar p is congruent to 0 mod p, and this is the expression that you are going to get. And after that, you can separate this quantity. Here the left hand side is mn bar p minus m bar p into n bar p, and this is the quantity on the left hand side can be separated for what? For evaluating its values, its possible values. For evaluating the possible values, we take that quantity, and then we can substitute the values, the possible values at the three places. For example, here one of the values, here you can consider 0, then 0. When we consider 0 and suppose that here this quantity equal to 0, then irrespective of the value, actual value of the third quantity, then you get that 0 minus 0 equal to 0. So 0 is one of the values that you are going to get. Next, you can assume that this quantity is equal to 0, but this quantity equal to plus 1 and this quantity equal to plus 1. Then the combined value will be 0 minus 1, 0 minus 1 equal to minus 1. So this way, you can find out all the values. You can find all the values belonging to this, related to this. Then you can then see that by considering all values of the legendary symbol, then we can see that then by considering all the possible values, then we can see that mn bar p minus m bar p into n bar p can take only the values either 0 or plus 2 or minus 2, and these are the possible values, because you cannot take here the plus 1 minus 1 without thinking about the product, this quantity mn. When m bar p has is assumed to be minus 1, that has some effect on this quantity also. So when this quantity is minus 1, then you have to consider the quantity according to that selected value of minus 1. So when we apply all the effects of these various values of the legendary symbol, you can see that you are going to get either 0, plus 1, or plus 2 or minus 2, and for the entire quantity. And also this statement says that p can divide the quantity. Actually, then here p, what is p? P is an odd prime number. So p can have the values either from varying from 3 up to it can go up to infinity. Therefore it cannot be the number p. Since the number p is an odd prime, it must be, it cannot be 2, and that is the important thing, and that number, the prime number p, cannot be equal to 2. Therefore the possibility, and also the possible values of p starts with the value 3, and it may be 5, it may be 7, and like that it goes up to infinity. Therefore you can clearly say that you can state that clearly this quantity cannot be equal to plus 2, or it cannot be equal to plus 2 or minus 2, because this statement says that p must divide the quantity, the final value of the quantity mn bar p minus m bar p into n bar p. And therefore, So that removes the possibility that the quantity equal to plus 1 or minus 1. Sorry, plus 2 or minus 2. So out of the three possible values, 0, plus 2 or minus 2, we have this. We can now eliminate the value plus 2 or minus 2. Hence, it comes clear that. So it becomes clear that the final value of the quantity is equal to 0. So since the value equal to 0, always whatever various values of whatever maybe the variations of the different Legendre symbol values, we are going to get the final value for the entire expression equal to 0. You can say that mn bar p is equal to m bar p into n bar p, and by this we are coming to the end of that result. Therefore you can always write that mn bar p is equal to m bar p into n bar p. That is the end of the steps of the proof. Okay, thank you.